tardes a todos. Bienvenidos a una nueva edición de los Coloquios IB. Hoy tenemos el gusto de presentar a Prem. Él viene de la Universidad Nanyang de Singapur, ¿sí? En particular, Prem, él es orador distinguido de la Sociedad IEEE, de la rama magnetismo, ¿sí? En particular, este programa de la IEEE elige a cuatro investigadores, básicamente, ¿sí? De todo el mundo, ¿sí? Y estos cuatro investigadores tienen la posibilidad de presentar una charla por todos los continentes, ¿sí? Ese es el programa. Y bueno, Prem, como uno de sus lugares que ha elegido para contar esta charla, bueno, el Instituto Balseiro, ¿no? Y la Comisión Nacional de Energía Atómica. Así que bueno, tenemos el agrado de recibirlo acá, ¿sí? Y ahora, bueno, va a ser la presentación formal Luis Avilés, que es el investigador hospedante, digamos. Así que bueno, Luis, te paso el micrófono para que lo presentes a Prem. Gracias.
Bueno, gracias, Julián. Ahora tengo el gusto de presentarles a quien amablemente voy a introducirles como Prem. Prem es profesor investigador del NTU. Él recibió su doctorado del Instituto de Tecnología de India en Bombay en el 1994. Luego realizó investigación en la Universidad de Shinshu, en Japón, entre el 95 y el 99, y trabajó en el Instituto de Almacenamiento de Datos de Singapur. Actualmente es profesor del NTU, como les mencioné, tiene 30 años de experiencia en magnetismo, trabajando en distintas ramas, principalmente en aleaciones magnéticas amorfas, materiales magnéticos permanentes, películas delgadas, en espintrónica y nanoestructuras para el almacenamiento de la información. Su interés o sus intereses principales abarcan áreas de magnetismo, electrónica y nanotecnología. Ha recibido premios por la excelencia académica del NTU y varios reconocimientos del DSI de Singapur. Hoy viene a presentarnos su trabajo titulado Brain Inspired Computing Based on Domain World Devices como Distinguished Lecturer de la IEEE de la rama de magnetismo. So, Prem, you can start whenever you want. Okay.
Hello. Thank you very much for the kind introduction, and thank you for inviting me to this symposium that you have every Friday. It's my pleasure to be here, and as a part of the IEEE Magnetic Society Distinguished Lecturer, I'll be talking about brain-inspired computing based on domain wall devices. So since my trip is supported by IEEE Magnetic Society, I would like to give some introduction about the IEEE Magnetic Society. So it has been there for around 60 years, and the IEEE Magnetic Society has around 3,000 members globally, out of which 10% are student members. So IEEE Magnetic Society publishes journals like IEEE Transaction Magnetics Letters, and IEEE Access. In addition, it also publishes books under the IEEE Wiley Press. So I am one of the book press, press license for this. So if anybody is keen to publish a book, just contact me. So I can link you with Wiley, then we can think about publishing a book. In addition to publications, IEEE also organizes conferences regularly. So Intermag is one of the premier conferences of IEEE, and in addition, in collaboration with the AIP, we also organize the Magnetism and Magnetic Materials Conference. So IEEE supports students and travel, the student presentation, and so on. And IEEE Summer School is one of the school where the students can benefit. So in 2024, this will be held in Taiwan. And IEEE also supports IEEE distinguished lecturers like me. So with that, I'll move on to introduce my lab. So my lab is called the Spin Lab. Basically, we are working on magnetism and magnetic materials, particularly with applied magnetism in mind. So we have two sputtering equipment, so we can make thin film samples based on these two tools. So with this machine, we can make 6 different layers, and with this machine, we can make around 11 different layers. And we can do lithography using these two lithography tools. So this is an optical lithography tool with a 1 micrometer resolution, and this is a nanofraser lithography with a resolution of around 300 nanometer. And we can do ion milling after fabricating the lithography steps. We can do ion milling here. So we can make devices, then test them using these tools. So we have an array of fabrication, deposition, and characterization tools. So most of the studies that we can do ourselves within our lab. So in Singapore, there are around 10 to 15 researchers on magnetism. All of them have their own group. All of them they have their own equipment, and these are the equipment that I have in my lab. And we have 5 PhD students, 2 postdocs, and 1 engineer working on different aspects of spintronics. Before I get into my talk, I also would like to thank the funding agencies, A-STAR and NRF of Singapore, who provided me the grant to work on neuromorphic computing. And these are my students and collaborators from different parts of the world. I had one slide of the Singapore map, but I lost it. Basically, Singapore is a tiny country in Asia. So it's if you look at the map, if India is here, China is somewhere here, Malaysia will be here. So Singapore is the one small country just at the southern side of Malaysia. So we call it little red dot because if you place a dot on Singapore to represent the Singapore in map, you cannot see the country. So it's such a small country. So we call it a little red dot. Maybe let me close and open the correct file. I don't know if this is the correct file. Yeah, this is the correct one. Yeah, so this is where Singapore is. So Malaysia is somewhere here, then Singapore is here. NTU is located at the western side of Singapore, somewhere in here. So basically, NTU is a school with all disciplines. So we started as an engineering university, then we moved on to do science, social sciences, and even medicine. And we have 32,000 students, out of which around 6,000 students are doing masters or PhD. Then we occupy an area of 200 hectares, and ours is a green building with a lot of solar cells. So if you look at the rooftop of all of the buildings, we'll have a lot of solar cells. So we wanted to go green by 2030 to be self-reliant on electricity by using the solar cells. Okay, so this will be the outline of my presentation. Since there are many of you from different backgrounds, I'll spend more time on the introduction and the fundamentals. Then later I move on to describe the work that we have carried out on synapses and neurons for neuromorphic computing. So we have all been using artificial intelligence application for almost a decade now. So either Siri or Alexa, we have been using some form of artificial intelligence. And with the introduction of ChatGPT a few years ago, I think almost everyone is using artificial intelligence. So artificial intelligence may not be just for productivity of common people. It can also enhance the research. For example, in the case of biology, for example, I was told that it takes 5 years of a student's PhD work to crack one protein. Okay. But with artificial intelligence, now people have cracked the structure of 200 million protein. That saves like 1 billion years of a PhD life. So this is how influential the artificial intelligence can be. And we are bound to be more benefits from artificial intelligence. So artificial intelligence works based on neural networks. So in the neural network, you have like input neurons and there are output neurons, and in between you may have several hundreds or thousands of hidden layers of neurons. So in the case of ChatGPT, for example, the connection between this neuron is around 100 trillion. So that's how the ChatGPT work. And if you look at the way things work, there is lots of data back and forth, lots of data flow back and forth between different neurons. So for example, this neuron is connected to all the neurons in the other layers and so on. So there is a lot of flow of data back and forth between different neurons. And this causes a problem because of the architecture that we have been using, which is the von Neumann architecture. So if you take a desktop, for example, we have a CPU, we have memory in the motherboard, and this CPU and memory are separated from each other in the motherboard. For example, the spacing between these two may be around 4 centimeter in the case of a desktop. So compared to the size of 40 nanometer transistor, this 4 centimeter distance is like a human having to travel 1,000 kilometers to fetch something. Okay, so that's the kind of distances we are talking about. So when data has to flow back and forth between these two units, so there is a joule heating and power is wasted, and time also is longer. So there is a delay in the data propagation, and there is power wastage and so on. And this is what this is one of the problems of the current way of doing artificial intelligence. So in that sense, people are trying to take inspiration from the brain. So we know that brain is intelligent. So in the recent past, a few years ago, people used supercomputer to play the game of Go with a human being. So for the first time, around 5 years ago, the supercomputer beat a human in playing Go. So in that case, if you take a supercomputer, it uses like 30 megawatt of power. However, our brain just uses 20 watt of power. So brain may be a bit slow, brain may be a bit less capable of doing lots of computation, but it's very energy efficient. So in that sense, we are trying to get inspiration from the brain to form computing system, and that's what is called neuromorphic computing. So compared to the current way of artificial intelligence, the new computing technique, which is neuromorphic computing, we need to come up with new methods of computing and new hardware elements. So that's what I'll be focusing on in my presentation. Okay, so having introduced you to the concept of neuromorphic computing, I'll now describe the fundamentals of the neuromorphic computing. Since it's about brain-inspired computing, we need to know what brain consists of. Although the researchers don't know how exactly the brain does the computing, people know that the neurons and the synapses in the brain are responsible for computing. So in this picture, this is a neuron, and the neuron, this is another neuron, and the connection between the two neurons happen through synaptic terminals. So these are the points of connection between two neurons. And in the computer analog, neuron is like a processor. So it basically gives rise to a spike when critical potential is reached and so on. I'll explain later. And the synapses are like the memory. And we have to build the electronic analogues of neurons and the synapses. So let's look at the neurons and the synapses in detail. So to understand neuron, we can consider a water tank as an analogy. So let's say you have a water tank with multiple inlets, and this water tank also has a hole, so it can leak water. Okay, so suppose there is water from only one inlet, so water will enter and water may leak, and the water level may not rise rapidly. On the other hand, if there are inputs from many of these inlets, then the water level can reach certain threshold. And if the water level reaches this height, for example, this will become like a funnel, and the water will drain out. So this is exactly how the neurons will work. So in the case of neuron, this inputs is a electrochemical signal. So basically neurons will receive inputs from many other neurons. So these are the inputs from many other neurons, and the neuron will integrate the received inputs, and if the total signal exceeds a threshold, the neuron will get excited and it will produce an output. So that's how the neuron function. I'll play a video to explain the concept of neuron. So this video is from the Christmas lectures of Royal Society, London.
I need to think about two things. How hairy was that animal in the picture? How big was the animal in the picture? I want you to think about those things in terms of like a scale of 1 to 10 while I explain what's going on over here, okay? So we've got these two containers that we can pour water into through these funnels. You can think of these like neurons. So this needs to be able to identify if something is hairy or not. This needs to be able to identify whether an animal is big or not. We'll start with hairiness. Question 1, on a scale of 1 to 10, how hairy was the animal in the picture I showed you?
I think about 8.
About an 8, okay. So we've got all these beakers of water here, but they're labeled 1 to 10, and you can see the amount of water goes up as the number goes up. So you chose 8, right? There we go. So that's quite a lot of water. So take that, and I want you to pour that into your funnel. Can you reach that? Yeah, just about, okay, great. Yeah, keep going, that's fantastic. So, because you chose quite a lot of water, the level should be able to rise to at least this funny little U-bend here. I want you to watch what happens when it gets there. Look at that. So that channel has now turned into a siphon, and the siphon effect is pulling all of the water out of this neuron and dumping it.
Simple model of 3 neuron circuit. So you can consider this as one neuron, this as another neuron, and this is as a third neuron. So here you saw that the input was actually the girl was pouring water. That was the input. So when the input exceeds certain threshold, the neuron completely gets excited. Basically, it means it transfers all the water to the other neuron. So similarly, in the case of brain or the neuromorphic computing circuits that we are going to use, the neurons will receive input from many other neurons, and if the signal exceeds certain threshold, it will release a pulse, and it will release a pulse, then it will go back to the resting potential. Like the water got completely drained out, so this potential will come back to the ground state. So this is what we want to achieve. So when we have to build the neurons, the electronic counterparts, they have to exhibit a similar behavior. So in the case of neuromorphic computing circuits, the components that we build, they will receive electrical inputs from many other neurons in analog-like manner. And finally, when the received signal is more than certain threshold, they will produce a digital-like output. And if you notice the video that I just played, it lacked one component that I have mentioned before. In the water tank analogy that I gave you, there was a hole that leaked water, whereas in the video that you saw there was no leaking component. So the leaking aspect also is one important aspect of the neuron. So for example, let's say this is some parameter. Let's say it can be water level of the beaker, or it can be a physical property X. So when this particular neuron receives an input, the property changes. Then when there is no input for this period of 10 nanoseconds, there is no input, so the property leaks. And when there is another input, again the property changes, and when nothing happens, there is a leak, and so on. So we should also consider the leaky aspect of neuron when we design a neuron. So, and finally, when all these 5 inputs made the parameter X to go above certain threshold, then firing of the neuron happens, then the neuron goes back to its ground state. So this is how we should design a neuron. And when we talk about synapses, in the case of biological synapses, synapses are the connection between 2 neurons, and the synaptic connection is made through neurotransmitters. So these are basically chemicals, and these chemicals make it easier or tougher for the information to be transmitted from one neuron to the other neuron. So to understand this concept easier, again let's take an analogy. Let's say we have 2 cliffs. Okay, so we have 2 cliffs, and the cliffs are far away. So let's say first time you want to go from one cliff to another cliff. Maybe you throw a rope, maybe tie it to a tree, then you hang onto the rope and cross across the cliff and reach the other cliff. So when you come back, let's say you throw another rope, then with 2 ropes you hang around, then come back. So first time, second time is difficult, but if you keep doing, every time you throw a rope, then tie the rope, then finally you may be even able to build a rope bridge with which you can walk easily. Okay? So by multiple repetition of connection between 2 neurons, the synaptic path becomes easier. So that's how our learning works. So first time when we learn, the topics are difficult, but if we keep learning the same topic many times, let's say mathematics, you do the sum many times repeatedly, you get familiarity with the concept of mathematics. So that's how the synaptic connections work. So when we are talking about the electronic counterparts of synapses, we are looking at devices whose resistance can be varied electrically. For example, like the cliff example I showed you before. Maybe in the beginning, the resistance between the 2 neurons is high, but as learning happens, the resistance may become lower and lower. So we should be able to vary the resistance, and this resistance should have multiple values. So it cannot be just 1 or 0 like in digital recording or digital memory. So we want some device which can have multiple values of resistance. So in that sense, people from different backgrounds are looking at synapses. For example, resistive random access memory can give rise to multiple values of resistance. So similarly, ferroelectric materials, phase change materials, all can give rise to multiple values of resistance. In today's talk, I will focus more on spintronics domain wall devices for making synapses. Okay, so I will now start with some basics of magnetism for those who are from different background. So we know that magnetic materials have north pole and south pole. So how you form north pole or south pole depends on how you fabricate material. In some materials, like for example, you take a hard disk recording media or magnetic random access memory. So in these devices, the magnetic materials are in single domain. For example, you have tiny nanocrystallites. Each of them are like magnets, and they switch independent of each other. So those are called single domains. So in this case, for example, if you look at this video, so when we apply a magnetic field, some grains switch first, some grains switch later. So they switch independent of each other. So this is called single domain switching or Stoner-Ulford switching. And this is the concept used for most of the applications, mainly the high technology application like hard disk media or magnetic random access memory. On the other hand, if you prepare a thin film of magnetic materials without any specific preparation technique, then the magnetic materials may form magnetic domains. For example, the black may represent north pole up, gray may represent south pole up. So when you apply magnetic field, the region with north pole up may expand. Okay? So the black and white regions are called domains, and the reversal of magnetization from north to south can happen by the motion of the domain walls. So this is called domain wall motion mechanism. So far we have been mainly using this property for application, whereas we didn't use the domain wall property much for application. However, in the past there are concepts like racetrack memory where people try to use the domain wall motion as a useful property. So before I get into that, let me describe how the magnetic random access memory works, because this will be the basis for the concept that we are going to discuss in the next few minutes. So the magnetic random access memory uses a device called the magnetic tunnel junction. So magnetic tunnel junction has two ferromagnetic layers. So one ferromagnetic layer is here, there is another ferromagnetic layer here, and they are separated by a magnesium oxide barrier. So here I have used the color code pink and blue to represent magnetization in the same direction or in the opposite direction. So here the two magnetization are in the same direction, and when we have this kind of configuration, the tunneling of electrons from one ferromagnetic material to the other ferromagnetic material is highly probable. So the resistance of this configuration will be low. And when we have magnetization in the antiparallel configuration, so let's say this is north pole, this is also north pole, then the probability of electron tunneling is less, so we'll have high resistance. So this is the building block of magnetic random access memory, and with this kind of magnetic tunnel junction, we can store only 0 and 1 state. So as I mentioned, this is a single domain kind of state, and I always give the analogy of Oreo biscuit for magnetic tunnel junction used in the MRAM. So like this is the one ferromagnetic layer, this is another ferromagnetic layer, and this is the magnesium oxide layer, and this Oreo biscuit can only store 0 and 1 state, and this is not enough for achieving the synapses that we need for neuromorphic computing. To achieve the synapses, we need multiple states. So we want 0, 0, 0, 0, 0, 0, 1, and so on. We want multiple resistive states. So to achieve that, we have to look for other types of magnetic tunnel junction, which I call KitKat like magnetic tunnel junction. So instead of Oreo biscuit shape, now we have a KitKat shape. So here again you have a magnetic tunnel junction, two ferromagnetic layers separated by magnesium oxide layer. So in this case, we can have domain walls. So this is not a single domain state. So here we can have multiple domain states. So in this case, one of the layer is called reference layer. So this layer's magnetization is always the same. So here the arrow is pointing up, so north pole is up, south pole is down. So this polarity doesn't change. Whereas the polarity of the layer here can be changed by sending some current through this part. Okay. So, we can have like fully parallel magnetization configuration or fully anti-parallel magnetization configuration, or a fraction of parallel and a fraction of anti-parallel magnetization configurations. So, this kind of configuration can lead to multiple resistance state. So, this is the concept that we proposed like 10, 11 years ago. So, this was meant for multiple bits in a memory cell, but we realized that this can be used for neuromorphic computing also. So, with that fundamentals, let me move on to describe how we can make the neurons and the synapses for neuromorphic computing. Okay, so in 2013 we proposed the KitKat like domain wall device, and in 2017 a group of computer scientists from Purdue University led by Professor Roy, they came up with a circuit of neuromorphic computing circuit based on domain wall devices that we just discussed. So, here for example, you can have lots of neurons and synapses connected in such a crossbar array to perform neuromorphic computing, and you can have two different types of neuron and some type of synapses here. So, we'll see this in detail. Okay, so based on the magnetic tunnel junction concept that I just described, we can actually create two types of neuron. One is called a step neuron, another is called a spike neuron. So, the difference you can see clearly from the pictures that I show here. In this spike neuron, the magnesium oxide layer and the reference layer are only in the right hand side, whereas in the step neuron, the magnesium oxide and the reference layer are there throughout the magnetic tunnel junction. So, when we have this kind of configuration, for example, when you send current through the spin orbit coupling material, the domain walls will be moved. So, we can vary the proportion of parallel and anti-parallel magnetization, and as a result the output will grow steadily. So, that is what is called a step neuron. On the other hand, in this spike neuron, if you move the domain wall from here to here, nothing will happen. But when the domain wall crosses here, then the resistance of this the magnetic tunnel junction will change. So, basically we will see a spike. So, this is how the spike neuron behaves, and the human neurons also work on the basis of spike. Okay. So, for neuromorphic computing, most likely we will be using this kind of spike neurons, and this is how we can prepare a spike neuron based on domain wall device. And how we can create domain wall synapses is again based on magnetic tunnel junction. For example, we can have two ferromagnetic layers separated by magnesium oxide, and we can have some kind of a spin Hall layer to move the domain wall. While the magnetic tunnel junction used for MRAM store only 0 and 1, these kind of domain wall devices can show multiple resistance state. For example, fully parallel can be low resistance state of around 1000 ohms, and a fully anti-parallel state can have high resistance of around 3000 ohms. And if you have intermediate positions, we can have different resistance. And we can move the domain wall by sending a current through the spin Hall layer. If there are any questions, you can feel free to ask me anytime. You can interrupt. Okay, so I don't want to keep talking. Please feel free to ask questions. So, we can move the domain wall because domain wall motion is the important concept to change the synaptic weight or to create a spike in the neuron. So domain wall motion is an important aspect of this neuromorphic computing. So we can move the domain walls by applying a magnetic field. We can send the current through the film and create a spin transfer torque. So that's another way of moving domain wall. The third way of moving domain wall is by sending current through a heavy metal. So this heavy metal will cause a spin polarization, and this spin polarization can be used to move the domain walls. So there are three types of techniques. So in the laboratory, it's always easy to do the magnetic field method. So you just apply a magnetic field using the electromagnet that you have in the lab. You can move the domain walls. So this is the easier thing to do, but this is energy inefficient and it's not practical for devices. But we'll do some of these studies using this technique because it's easy to do. And for industrial application, this is the better method because this is the most energy efficient method. So compared to spin transfer torque, this consumes even lesser energy. So domain wall motion has a different terminology when we talk about different devices. So when we talk about neuron, we call the domain wall motion as integration because this is very similar to the process done by human brain. Human brain acquires signal from different neurons, then it integrates and gives an output. So we call the domain wall motion in the neuron as integration. And in the case of synapse, the domain wall motion can change the weight. Weight is basically the connection between two neurons. And the current for the domain wall motion comes from the spike of the other neurons. So that's how the neuromorphic computing works. So what physicists or material scientists can do to advance the spin-based neuromorphic computing, we can look for higher and higher values of tunnel magnetoresistance. So this is one way, but it's not easy path. Then we can also find out materials or mechanism that can drive domain walls at low energies. So spin-orbit coupling is currently used. Whether we can use orbital torque to move the domain walls at even much lower energy. So these are some questions that material scientists or physicists can have. And in the case of synapses, we should look at achieving multiple resistive states in our devices. So in that sense, domain wall pinning mechanism will be efficient, will be useful. And when we design neuron, we have to find out how we can achieve the three function, leak, integrate, and fire functions of neuron. All these are jargons to people who are not in this field. I'll explain this later. But these are the things that we are aiming at to make the spin-based neuromorphic computing realistic. How much time do I have? Like 25 minutes? 35 minutes. How long? More? 10-15 minutes. Okay. So I'll just touch upon two of the work that we have done. So normally if you magnetize the material and reduce the magnetic field, you are supposed to form domains and the domain should move. But in this example, let's say we have cobalt palladium multilayers in the form of a device. And here we have saturated the material with a high positive magnetic field. And when we go back to the negative field, nothing happened, no domains formed. And at a negative field, slightly larger value of negative field, the material completely turns into the other polarization. That means no domains are formed. We couldn't move form or move domain wall. So this implies that we need to come up with some domain wall pinning mechanisms. So we have studied various methods of domain wall pinning mechanism. So we basically classify them into two different approaches. One is magnetic approach, where we change the magnetic property of the material without any structural change. Or in the other case, we may have some structural change like this. We may have different segments offset from each other. So here magnetic property is the same throughout the material, but structurally there is a change, so we call them as a geometric. So with this kind of approaches, we can create domains and we can pin the domain walls and we can move the domain walls in a controllable manner. So this is an important step of forming synapses using domain wall devices. So basically all these domain wall pinning processes work either by creating an energy barrier or an energy well. So in the first case, when the domain wall enters this energy hill, it will stop here. In the other case, the domain wall will reach this barrier and it will stop here. You can find out whether you are forming energy hill or energy valley by looking at where the domain wall motion stops, where the pinning strength is stronger. So today I will just focus on one topic which we haven't shown before. So this particular synapse that we have prepared is called a pine tree synapse because it looks like a pine tree. So in this case we are using the Laplace force as a mechanism to pin and control the flow of domain walls. So you have two torques. One, suppose you send a current through the spin Hall material, you have a torque from the spin orbit torque, and you also have a Laplace torque. And if these two balance each other, the domain wall will get stuck. But if one of them exceeds the other, the domain wall will move. So we have carried out micromagnetic simulation of these kind of pine tree structures with different weights, different lengths, and so on. And we have calculated that, we have interestingly observed that this kind of devices show easy and hard direction. That means it's easy to move domain walls from left to right, and it's hard to move the domain walls from right to left. So this is also kind of a domain wall diode. So you can see that the current required to move the domain walls from left to right is lower, and in the hard direction the current is larger. And the Laplace force also can be calculated from the micromagnetic simulation, knowing the material properties, DMI, anisotropy, exchange constant, and so on. We can calculate the Laplace force, and the Laplace force is uniform from right to left, and the left to right it has different values depending on the ratio of WL and the width WS. Okay, so these are simulation studies with which we have already shown that the pinning is possible. Whether we can achieve this experimentally is a question. So we fabricated samples of this type. So this is a cobalt iron boron material with a perpendicular magnetic anisotropy. So we fabricated devices with a different ratio of width 3, 2, and 1.5. This was done using optical lithography, so the width of the smallest part was around 10 micrometer. So here again we tried to move the domain wall with magnetic field, and we could observe pinning at this corners. Then we also tried to move the domain wall by spin Hall effect. So in this case, we apply an HX to break the symmetry, and we send a current of this magnitude. So for smaller ratio, we could move the domain walls with this kind of current density uniformly, and for larger ratio, we couldn't move the domain wall even with a larger current density, and it was also found to nucleate some domains because of Joule heating, because there are some regions with narrower width. So the current density here is larger, so heating happens, and because of Joule heating, some nucleation of domains happen. So these results give information that optimization of this, the larger width and smaller width, is the key to control the flow of domains. So in the study that we have done, I have only focused on the free layer. Okay, so the free layer position is basically the indication of resistance. So if the magnetization of the reference layer is a fixed constant, the free layer position will determine the resistive states, and you can see that by changing the domain wall position, we can change the resistance value. So this is one way to form synaptic devices using magnetic domain walls based on magnetic terminal junctions. Okay, so now I move on to explain our work on neurons. So neurons should basically exhibit leaky integrate fire functions. So integrate is basically the neuron under discussion is receiving input from many other neurons. So the domain wall is pushed by current. Okay, so this is not a complex concept. This has already been used in the concept of racetrack memory proposed by Stuart Parkin. So this is straightforward, and the fire function is achieved when the domain wall reaches here and there is a MTJ, magnetic terminal junction, and the resistance value changes. So that's also not a tricky part, because the read sensors of the hard disk drives and the MRAM basically rely on reading signal based on the resistance of magnetic terminal junction. So there is nothing new here. So what's new, what is challenging to be achieved is the leaky aspect of neuron. Whether in racetrack memory or the domain wall devices that we have proposed before, there is no leakage function. If you move the domain wall from one position to the other position, the domain wall will get stuck here, it won't go back. So for leaky function, we want the domain wall to return back to their original position. So we move the domain walls here, the fire function is achieved. So after fire function is achieved, the domain wall should go back to the initial position. So that's the key challenge of neuron. So for that, we have worked on various designs. So in one design, we have neuron with an anisotropy gradient. For example, physically or topographically, the domain wall device will look similar from left to right. But in terms of physical parameters, there may be a gradient in the anisotropy field. So we may change the Ku or Ms of the material or both to achieve a change in anisotropy field. For example, low anisotropy field here and high anisotropy field here. So there is a gradient in the anisotropy field. So when you have a gradient in the anisotropy field, you move the domain wall first, and when you release the domain wall, because of this gradient, the domain wall will return back to its initial position. So that's one way to achieve leakage function. Another way to achieve the leakage function is to have stray field neuron. So in this case, again, this is the layer of interest of neuron. So we move the domain wall from here to here, and when we achieve fire function, basically there is another hard layer which produces a magnetic field. So this stray magnetic field will push the domain wall from here to here, making this whole thing parallel to each other. So these are some ways to achieve leakage. Today I'll talk about another concept called synthetic antiferromagnetic neuron device. So in this case we have two ferromagnetic layers which are antiferromagnetically coupled through the presence of a thin ruthenium layer. So if you have two ferromagnetic layers separated by a thin ruthenium layer, you can have antiparallel coupling, which is the concept of synthetic antiferromagnetism. So if you have such synthetic antiferromagnetism, you move the domain wall by say some current, and once the fire function is achieved, you remove the current, the domain wall will return back to its own position. So this is the leakage function that we want to see experimentally. And this can be, this is a demonstration of the leakage function using simulation. Let me show a few results that we have achieved using experimental techniques. Okay, so to fabricate and demonstrate leakage function using synthetic antiferromagnetic coupling, we created this kind of structures. So here the bottom platinum layers are meant for driving the domain walls, so they are heavy metal for spin orbit coupling, and we have cobalt platinum layers as one layer, one ferromagnetic layer here. Then ruthenium is meant for producing the antiferromagnetic coupling. So by varying the thickness of ruthenium, you can achieve different strength of the antiparallel coupling. So we actually see three peaks, and the lowest exchange coupling is here, the highest exchange coupling is observed at 0.5 nanometer ruthenium. And to achieve the leakage function, we fabricated Hall bar devices which look like this. So here I have color coded the Hall bar device to match the ferromagnetic layer at the bottom, which is pink color, and the ferromagnetic layer at the top, which is the cyan color. So we purposely designed the device like this because we want to create a reverse domain here. So here only the bottom layer is present, so we can nucleate a domain here and move this domain to this part. And when this domain wall reaches here, we call that as integration. Then we switch off the current, then the domain wall will come back. So that is the leaky function. Okay, so here again I show the color code. For example, I don't know if you can see, there are two kinds of pink. So one is like dark pink here. So dark pink means they are antiparallel. So by sending current or magnetic field, we can move this dark pink to the right. And once we remove the magnetic field or current that drives the domain wall, it will come back to its position. So we measured this change in the domain wall position using anomalous Hall effect measurement, and that's what is shown here. So when the two layers are completely antiparallel to each other, we have a lower Hall voltage, and when the domain wall is moved somewhere here, then we have a higher Hall voltage, and when we remove the current that drives the domain wall motion, the domain wall comes back to its initial position, indicating the leakage behavior. Okay, so the concept may be difficult for someone who follows this work for the first time, but basically you can understand that this is the integration process, and this drop in the anomalous Hall voltage is the leakage of the neuron structure. So with this stack, we showed the integration and the leakage property. We even tried to measure how fast the domain wall comes back from this position to this position. So for that, we created another type of device where we can measure this distance and the time taken for the domain wall from here to reach from here to here. So that way we can measure the domain wall velocity, how fast it leaks and so on. So that leakage velocity depends on the exchange field. So if the exchange coupling between the two ferromagnetic layers is strong, then the leakage velocity is faster. And if the exchange coupling is weaker, then the domain wall returns slowly. So these are the kind of work that we have done on neurons. So as conclusions, we have shown synaptic behavior of domain wall devices using anomalous Hall effect. Ideally, we have to make magnetic tunnel junction and show that multiple resistance states can be achieved. But AHE is a shortcut to show the synaptic behavior in a university laboratory setting. And the leaky integrate fire function of neuron can be achieved through various configurations. So I showed you 3 different examples, although I didn't spend much time on that. And for future, researchers may focus on improving the spin orbit torque efficiency, because that's one way of doing energy efficient neuromorphic computing. And a bottleneck for spin-based neuromorphic computing could be the tunnel magnetoresistance. So in the fabs, people can achieve 200% TMR. So with 200% TMR, if you have 8 states, you may have like only 25% change in the resistance, which will be around 250 ohms in the case of magnetic tunnel junction, which may be a bit too less. So people either need to increase the TMR or they need to find out some way to tackle that. Even though your resistance change is small, whether you can make meaningful decision is another topic for research. So with that conclusion and outlook, I will end my presentation. Thank you very much. Thank you.
Very much, Prem. Well, okay, we open the session to questions.
Thank you, Prem, for this amazing talk. I really like the different results you show. I have a few questions. One, for example, is how do you control the anisotropy, or how do you get a gradient of anisotropy in your nanowire?
Okay. I presented that work in Intermac before I came here. So there are a few ways to do. So if you want to have anisotropy gradient, one easy way to do is by having wedge structure. So you can have magnetic films with a wedge kind of structure. So you know that in PMA materials, the thickness determines the anisotropy. So in regions with smaller thickness, you will have larger anisotropy, lesser thickness you will have lesser thickness you will have larger anisotropy, larger thickness you will have smaller anisotropy. So that's one way. In the work that I presented in Intermac, what we have done is we apply a voltage at one place to reduce the anisotropy locally. So you know that when you apply voltage, there's a voltage induced anisotropy change. So with that, you can also, by that method also you can create this kind of anisotropy. So that's more practical way of doing
it. I have another question. When you show the simulation and also the experimental results about the domain wall motion in your wires, it is possible to see that the upper part of the wire reverses before the lowest part.
So which work?
I think it's in 32, in slide 32.
32, is it?
Yeah. Yes, order, that one.
This one?
Yeah, that one, the second one. For example, you have that in the image close 10,
Okay.
in the central image of 10, the upper part of your domain wall rotates before the lower part. And in all the cases.
You
There.
mean here?
No, in the middle one.
This one?
Yeah.
This one may be an optical illusion, I think, because we are using a stage which may vibrate a bit.
Okay.
I think this is an illusion.
Okay.
I mean, one problem that we have seen here is this. We have like different junction. So even though you send a constant current, the current density is different at different points. So it hits at this region and creates this nucleation. Yeah.
Okay. I have another one related to the SAF. When you have the domain wall motion in your synthetic antiferromagnet, you apply a current pulse which generate in-plane torque, right? And that, is that correct?
Yeah, we send a current. Actually, moving the domain ball in this kind of material was not easy. So we have to apply
the field.
certain Hg also, because the exchange field was so strong that you have to apply a certain field in the G direction also. So we apply this field, then Hx, then a current for the spin orbit torque material. So all this together only could integrate. It was not easy. Yes.
Yeah, I understand. Okay, thank you.
More questions?
I was wondering what controls the time scale of the domain wall dynamics.
In the literature, people have studied the synthetic antiferromagnetic materials, like the one I have shown. So in such materials, people have reported the speed of around 1000 meter per second. Even if you don't have the synthetic antiferromagnetic structure, you can get 100 meter per second, that kind of speed. But in our case, I don't know, is maybe, I mean, we don't have sophisticated equipment, so the value we measure are much lower than what.
Okay.
Yeah. So I'm showing millimeter per second because we are using the same lock-in amplifier for measuring the position here and the other place. So there is some drawback in what we measure, but people have reported hundreds to thousands of meter per second.
So you can make it much faster.
Yeah, actually it's much faster. Yes.
Thank you for the talk. Is the dissipation an issue in these devices? I mean, with the current, what large of the current you can use or detect, or especially if you can change the resistance, is there a range where you cannot access because of the dissipation?
So your question is about the range of current that we can use.
Yeah.
Okay, so here there are two currents. One is for reading the resistive state, which is usually much lower in value. Another one is the current that we use for moving the domain walls. Whether it's neuron or synapses, we have to move the domain walls from one side to the other side. So for that, we are using the concept of spin orbit torque, where the current density is typically 10 power 10, 10 power 11 ampere per square meter. But we want to go as small as possible. If we can go to 10 power 8 ampere per square meter or something like that, it's better. So we are trying to go towards a lower direction.
Okay, more questions? Okay, we thank Prem again.
Okay, thank you very much. Thank you.
Los esperamos el próximo viernes, creo.